this video we're going to look at solids, liquids and gases. And we'll start off by doing a little bit of revision of probably one of the first things you ever did when you got to high school, which is look at the three states of matter, solids, liquids and gases, and name the changes of states. So we've got three boxes here, solid, liquid and gas. To move from solid, liquid and gas, we do that by heating the substance up. Okay, conversely, to go from gas to liquid to solid, we do that by cooling the substance down. Okay, change of state from solid to liquid is called melting. You need to know all of these. From liquid to gas, it's boiling. That's if we heat it up to its boiling point, or evaporating. Liquids will evaporate. Beneath their boiling point, it results in the same thing. The liquid turns to the gas. Gas to liquid, that's condensing. And from liquid to solid, that's freezing. Okay, now how are the particles arranged in each of these? First off, solid. Particles in solid are arranged in an ordered, regular fashion. So I've got one particle here. Let's try and make all the particles in a solid the same size. Now, different solids have different ways their particles are ordered, but we're just going to do a nice simple one here. This is how particles are arranged in a lot of metals. Okay, nicely in order, in rows. And this row is going to fit into the gaps of the previous row here, and then the third row is going to be back in the same sort of order arrangement as the first row. And you can fill that box up like that, like bricks in a wall, basically. In a liquid, let's do gas first. In a gas, particles are far apart, moving fast. Okay, I'm just going to do three. You can do them wherever you want in there. I'll put some little arrows, chevron things on the back of these. In any old direction, they move. They're moving around all the time, bouncing into the walls of the container, bouncing into each other. There's an expression about gas particles that always sticks in my head. They move with constant, rapid, random motion. Okay, now the liquid. Now, a lot of students get liquids wrong because what they do is they kind of do a hybrid between these two. They do them random and a bit closer, and that's wrong. Okay, it's wrong because liquids cannot be compressed. They cannot be squashed. You can compress a gas because there's space between the particles. You can't compress a solid because there's no space between the particles. Now, you can't compress a liquid because there's no space between the particles. The particles in a liquid must be touching. Now, having said that, they are randomly arranged because the particles in a liquid are constantly moving over one another. Okay, you pour a liquid into a sink, it takes the shape of the sink as it goes down the drain, the plug hole. It takes the shape of the drain. Okay, now if you draw particles as close together as you can, you will invariably end up with this solid arrangement because that's the best way they can go together. Okay, so there are going to be some spaces in the liquid, but on the whole, the liquid particles are going to be touching. Okay, so it has to be a random arrangement where the particles are still touching. So solid, liquid, gas. Again, need to know all that. Okay, so next page. There's a couple of different types of changes in chemistry. There's physical changes or chemical changes. A chemical change is a chemical reaction where particles are rearranged in the reactants to form products, new substances. Chemical bonds are made or broken. Often these changes are irreversible. Okay, changes of state like this are called physical changes because they are reversible. You can heat them up, okay, and you get to a liquid and a gas, and you cool them down, you can get back to the solid again. Okay, so we've got a few examples here. So snow melting, for example, that's melting, that's a physical change. Petrol burning, that's a chemical change. Paint drying. The solvent in a paint evaporates, that's why the room smells after you've painted it, but as it evaporates, the paint changes chemically and hardens. Okay, so even if you put the solvent back, you can't go back into that paint stage. Okay, plants photosynthesizing, they take carbon dioxide and water and turn them to glucose, that's a chemical reaction. Salt dissolving in water, dissolving is a physical because you can evaporate the water again. Glass breaking, what some people may say, that's chemical because once you've broken the window, you can't get it back again. Well, you can, you just have to melt the glass in a factory and turn it into a new pane of glass. So that very much is a physical change. Okay, explain in your own words how the particles move in the solid state and how an energy change can bring about the change to the liquid state. Okay, so a written explanation about particles and how they change. First off, then particles in a solid are not still, they vibrate. So if we go back to this, this diagram here of a solid, these particles are vibrating back and forward, okay? And all these are vibrating back and forward. And those vibrations are small, okay, with a little bit of energy, and so the particles are still locked in place because these particles attract each other, okay? And these vibrations are only small, so nowhere near big enough to force these particles apart, but they are vibrating the whole time. So particles in a solid vibrate. Now, as we heat the solid up, we can, when we get to the melting point, melt it. But as we heat it up, okay, so as a solid is heated, the particles vibrate with more energy. In other words, they vibrate faster, they vibrate with more force. Okay, now, at some point, as we heat it, those vibrations have got to become so strong, so big that the particles break apart. So let's write that. When the energy of the vibrations is large enough to overcome the attractive forces are forces of attraction between the particles, overcome the attractive forces holding the particles in place, they break free. In other words, they melt. The solid melts, and that means turns to a liquid. So let's just repeat that. Okay, these particles in this solid, they are held in place by attractive forces. That's what keeps them in this neat, orderly arrangement. Having said that, they are vibrating, wobbling back and forwards. As we heat them up, the vibrations get bigger. At some point, when we heat it to a large enough level, those vibrations become so big, these particles can break free and start moving around and turn into a liquid. Okay? Next one. Explain your own words how the particles move in a liquid and how an energy change can bring about the change to the gaseous state. Okay, so the particles in a liquid are touching, we've said that already, that's important, are touching but moving randomly around. Okay, so they're moving all the time. As a liquid is heated, they move with more energy, they move faster. So as you get them hotter, those particles move quicker, okay? Now when the particles are moving with enough energy, when we've heated them enough, they can break free from the other particles, okay, and that's turning to a gas, so let's write that. When the particles are moving with enough energy, and that's different for every liquid because every liquid has its own unique boiling point, they can break free. They can break free from the other particles. Okay, and that is when they turn to a gas. That's boiling or evaporating, turn to a gas. Okay, so the next couple of explanations are just the same but in reverse, so I'm going to leave you do those on your own. Okay, and what we've got here now is this table, and I'll do one of these, you can do the rest. It says, use the melting points and boiling points of the following elements to state whether they are a solid, liquid or gas for a stated temperature. Okay, so we've got argon here. We've got its melting point, and we've got its boiling point, and we want to know at this temperature, is it a solid, liquid or a gas? Well, think about this. Just draw yourself a number line up. Okay, and let's go for the lowest number to start with, minus 189. Let's put that there, minus 189.35. The next number here, okay, minus 185.85. Okay, so this is the melting point, the temperature at which it turns from a solid to a liquid. It's a solid when it's colder, so colder than minus 189 would be this side on the number line. So let's write solid here. So at this point on the number line, this is a solid. After we've warmed it up, because we're getting hotter as we come this way, so this way is hotter. Okay, as we get hotter, the solid will melt, and it melts at the melting point, minus 189. So once it's melted, it is a liquid. Okay, and then we're going to go hotter, And when we get hotter, we get to the boiling point, minus 185. And when it boils, it turns to a gas. So that's the three states of matter around this melting point and this boiling point. Now we're asking this temperature here 20 degrees. So you have to ask yourself, is 20 degrees, where's 20 degrees on this number line? Well, it's well up here. Okay, so eventually you're going to get to 0 eventually, and then maybe much later it's going to get onto 20 degrees. So 20 degrees is here. So we want to know what state it is here, and the answer is in the gas segment. So that is going to be a gas. Now these questions are quite simple when you know how, but you'd be amazed how many people really struggle to get their head around it. If you struggle to get your head around it, that's totally normal. It's totally normal. But can I just suggest you do a number line like this for each one of these until you get them right. I'll give you a clue about this one. This one's going to be a liquid. So see if you can figure out why. Okay, and you can have a go with the next ones. All right, next page. Last page on solids, liquids and gases. Okay. A solid substance is heated at a constant rate and its temperature is taken every minute. So the results have been plotted on the graph below. So here's time 0 down here, okay, and temperature, maybe there, okay. Say, whatever number it is. As time goes on, as time increases, the temperature warms up and then it goes flat. And then it suddenly starts to increase again, and then it goes flat, and it starts to increase again. Okay, now this substance is being heated the whole time. So the temperature rises, then it goes flat, rises and it goes flat. The reason it goes flat is its changing state. Okay, so let's label it to start with solid. Well, it's going to be a solid here before we start heating it. Okay, because it says a solid substance is heated. So it's a solid at the start, a solid's getting hotter. Okay, and then when it goes flat here, it is melting. Okay, you can always tell a change of state of a pure substance on a graph like this because the temperature goes flat. When there is a change of state, there is no increase in temperature, and that's important. Okay, after we've done that, we're heating it some more. Okay, and it's the liquid state now. So now here, when the temperature starts to rise again, it's the liquid state. Eventually, the liquid will boil. So that's where it's boiling. It gets flat again, and here it's the gaseous state. It's the gas. Okay, a little fill in the blanks about this. When the solid substance is heated, the temperature rises. The temperature stops rising and stays constant when the solid starts boiling. Sorry, solid starts melting. I'm ahead of myself, aren't I? Melting. The substance is still being heated, but the energy is making the particles break away from their fixed arrangement. Okay, so remember what we said here. These particles in solid are attracted, okay, but when it's melting, those particles are breaking away from each other. So all the energy we're giving this by heating this solid up is being used to break these particles away. That's why the temperature goes flat. And this bit here, you now need to do a similar explanation to this, but for boiling, and it's exactly the same. As you heat the liquid up, the particles move faster, but when we get to the boiling point, the energy is used to force the particles away from each other so they can escape from the liquid. Let's use that word escape down here. So in this answer here, let's use the word escape for why the temperature goes flat. Temperature goes flat because when we're heating it, all the energy is being used to give the particles the energy to escape from each other. And that's solids, liquids, and gases.